Welcome, my dear students, on a new lecture on functional analysis. In the previous lecture, we have discussed about the set of all bounded linear operators from a normed space x onto a normed space y. We have made it into a normed space with the norm which is defined on the set of the bounded linear operators, and we have already proved that this b of xy, which is the collection of all bounded linear operators from x to y, is actually complete whenever y is complete. Now, the similar terminologies can also be used in the case of linear functionals as well, because every linear functional is a linear operator. The only difference is that in terms of the space y, we are either using the set of all real numbers with usual metric and or the set of all complex numbers with the usual metric. That's the only difference. So we can use the similar terminologies which we have used in the set of all linear operators from x to y on the linear functionals as well. So let us define that. Let capital X be a normed space. Then the collection of all linear bounded linear functionals on X forms a normed space with norm of f is equal to supremum x element of capital X or d of f x not equal to 0 modulus of f of x by norm x, or supremum x element of capital X with the norm x equal to 1 modulus of f of x. The only difference is that instead of t we have used f, and f is a linear functional from x onto R set of all real numbers or complex numbers. So instead of using norm here, we have used the modulus. So using the same property as we have defined in the case of b of xy, using the same ideas we have used, we can easily understand that this is a normed space, and this normed space is called the dual of x, and it is denoted as x dash. So x dash is actually the set of all bounded linear functionals defined on capital X, which forms a normed space using this norm. The proof is actually same as the same proof in the case of the linear operators, bounded linear operators. The only difference is that instead of norm t, we are using modulus of f. That's the only difference. And using the previous theorem, which states that b of xy is using the theorem b of xy is Banach whenever y is Banach, we can easily state that set of the dual space is actually a Banach space. So we can state that theorem, the dual space of x is actually a Banach space, because here the set of all linear functionals is defined from X to R, and set of all real numbers or set of all complex numbers are complete spaces, which means that X dash is the collection of all linear functionals, which is a particular case of linear operators, from a normed space X onto the set of a complete space. By using this theorem, the set of all linear operators from X to Y is Banach whenever Y is Banach. Here, set of all real numbers or set of all complex numbers is actually a Banach space. So, from that, we can state the following theorem. The dual of a normed space X is complete. Dual is denoted as X dash, or it's a Banach space. The proof is, as this proof in the case of this theorem, you are only replacing y by set of all real numbers or set of all complex numbers. Instead of t from x to y, we are defining a functional f from x to r or c. Since r or c is complete, we can use this theorem to state that this is actually the complete. So the dual space of a normed space consists of the set of all linear functionals or bounded linear functionals from a normed space X, which is, and it forms a complete normed space, or it's a Banach space. That's the basic idea. So if you have been asked to prove this theorem, you have to prove this theorem and state the fact that here, in the case of linear functionals, y is either r or c. Both of them are complete. So by using this theorem, the dual x dash is always complete. So even though x is not complete, that its dual space is always complete. So whenever a normed space is not complete, you can make another normed space from that, which is the dual space, which is always complete. So that's the basic idea about the dual space. Now we have to get some idea about this dual space. That's our objective. The only thing which we know about the dual space is actually it consists of the set of all linear functionals, actually the bounded linear functionals defined on some normed space capital X. That's the only thing which we got up until now. But in some cases, in the case of let's say Rn or Cn, we have to know what is actually a dual space. So it is difficult to find all linear functionals which is defined on a particular space. Another way to identify a particular space is by identifying a similar space associated with that. So, to understand the dual of a particular space, it's a better way that if we proceed by identifying a similar space or an isomorphic space to the dual of a particular space. That's what we are going to do. So our objective is to understand the dual space of some particular class of spaces. But it is not easy to understand them, since dual consists of the linear functionals which is defined on capital X. We cannot find all linear functionals explicitly and understand them on a structure. But another way to do that is to find the space which is actually similar or actually isomorphic to the dual and identify with that. So there are dual spaces of some normed spaces which is actually very easy to understand by this idea, by defining an isomorphism from the dual space onto some other space. By means of that, can actually say that the dual space is actually a particular space. So, if we are defining a particular x, our objective is to understand x dash. So, what we are going to do is we are define an isomorphism from x dash to some y, which we already know. So, if you are able to define an isomorphism x dash from y, so which means that x dash is similar to y. Structurally, x dash and y are quite same. Now, every properties of y can be similarly defined on x dash. So, even though y is another space which consists of different set of elements rather than the linear functionals, by means of isomorphism, x dash and y are same. So, which means that even though these two spaces have different set of elements, maybe different operations in general, the properties are same. So, the dual of a particular space can be identified with another space by means of an isomorphism. So, that's the way to understand the dual of some spaces. That's what we are going to do. Before that, we have to understand what is an isomorphism means. So, our objective, please remember our objective is to understand the dual of some class of space. So methodology we are doing is by defining a similar space of that of the dual or by means of an isomorphism. An isomorphism from a normed space x onto another normed space x dash or x tilde is a bijective linear map which preserves norm, which means that for all x element of capital X, norm of Tx should be equal to norm of x, where T is the bijective linear map which we have defined from x to x tilde. So, two spaces x and x tilde are said to be isomorphic if there exists an isomorphism from x to x tilde, which is a bijective linear map T from x to x tilde, which preserves norm. That is, norm of the images of every element should be equal to norm of the element. So, if at all between two spaces x and x tilde, there exists a bijective linear map which satisfies or which preserves the norm, then we say that the two spaces are said to be isomorphic or and the function is called the isomorphism from x to x tilde. The basic idea behind defining such a notion is the fact that by means of an isomorphism, we can actually identify the properties or the structural similarities of the two spaces in general. So, if at all there exist two spaces x and x tilde which are isomorphic, then structurally they must be same. Even though their elements and their operations may not be the same, the properties are entirely same. So that is our objective. Our objective was to somehow understand the dual of some classes of spaces, which is not an easy thing. But what we are going to do is we are going to define an isomorphism from x dash onto another space y, which we already know. And if at all that is possible, then x dash should be isomorphic to that space y. Then Since we already know the properties of y, we can easily understand that x dash has the same set of properties. So that's why we define such a notion. And next thing, what we are going to do is we are going to study the dual space of some classes of space, especially that of Rn, L1, etc., and LP. We study these, the dual of these spaces by means of this idea. So we are going to study the dual of Rn, L1, and LP. That's what we are going to do. So which we'll be discussing in the next lecture. Thank you.